So we'll begin by taking a look at our calendar. Today is Friday, February 15th. Today we're going to finish up the two problems from the previous class that the last video didn't get to, and then we'll talk some more about computing volumes. Officially this morning, project number 4 is due, so hopefully you can slide that under my door by the end of class time today. Project 5 is now assigned. I handed that out in class on Monday along with 4 different chocolates, so you can get started on that over the break. So, and then one more reminder, the very first day we get back from break, that Monday morning, first thing we have is a quiz on classes 16, 17, and 18. So the quiz will be on those 3 topics right there. So let's go ahead and get started. We're here on page 25 in the packet, and we'll begin up at the top. It says, same as the last question. All right, so let's remind ourselves of what the last question was. So way down here. The last question was number 11, find the volume of a solid whose base is the region inside of the circle x squared plus y squared equals 4, and whose cross sections perpendicular to the x-axis are squares. So that's the problem that we did last time. And this time, we'll do the same thing, except it says the cross sections are now equilateral triangles. So let's start by drawing a picture. So we'll go ahead and draw our x-axis normal, but then to try to get that y-axis to go away from us, sort of into the page, we'll flatten it out. And then I'm just going to go ahead and draw my circle, except I'll just draw it here without putting hash marks. I'll put them at the end. So the circle is still going out 2 in every direction. And it looks more elliptical because we flattened out that circle. And now we want the cross sections to be equilateral triangles, and the cross sections are still perpendicular to the x-axis. So our cross sections are going in this direction out of the paper, out of the board, and all perpendicular to the x-axis. So now we want equilateral triangles. So for example, I can draw a cross section starting here. That side right there is in the circle. That's the base of my equilateral triangle, which means that the rest of the equilateral triangle comes out of the board and then goes back into the board, and it's an equilateral triangle, so all 3 sides are equal. And if I decided to draw another equilateral triangle out at this spot, now the base is smaller, so this equilateral triangle, as a result, is going to be smaller. So we'll have all of these equilateral triangles sweeping left and right, and maybe you can imagine that the shape will be mostly round like it was before with the squares, but in this case, instead of having 2 different kind of hard angled things at the top of this shape, we're just going to have one hard angled line going from the one side of the circle straight opposite to the other side of the circle. So I can't do a very good job drawing it, so we'll let the technology make up for my ineptitude, and we'll just take a look at this. Again, it's free software. You can download this. That's the name of this demonstration. Just go to just Google Wolfram CDF Player, and you can download it for free. So here's the shape. You can see the circular base is there, and all the cross sections are equilateral triangles. You can see the dark solid, the black lines are all the cross sections. Small equilateral triangles over here, very big ones in the middle, and then getting smaller over to the other side. And we're trying to find the volume of this crazy shape. So let's give it a shot. It's the same technique as before. We're going to imagine taking one triangle and sweeping it left and right. So let's go ahead and call that that bigger blue triangle, we'll call this a generic point X. That's this point right here. And now we're going to try to come up with a formula for the area of that triangle in terms of X. So one of the facts that we had from before was that if you have a problem where the cross sections are things whose area you know, then you can take that area function, it's a function of X, stick it inside of an integral, and churn through, and you'll get the volume of that shape. So the hard part here is to find this a of x. Find the area of the triangle at x, at some generic x. Okay, so we've got our generic x sitting in our picture, and if we're looking at the area of a triangle, well, I still know that the area of a triangle is half the base times the height, so we got to find these 2 things. So it seems like the base of this triangle, or one of the bases, could be, I'll highlight it here in green. So maybe this side right here in the circle, we can call that the base of the triangle. And then the height of the triangle, so the picture is going to get a little bit messy now, but the height of the triangle is going to be this dotted line coming from the top and going right down to the middle of that base. So that dotted blue line is the height. So we got to find the base and we got to find the height. So first we'll think about the base. Looking at that green line segment, would you say that that is a change in x or a change in y? Hopefully we see it's a change in y. The x is the same everywhere on this green line, but the y changes. So again, we want to know what is the y at the top, what is the y at the bottom, and whatever they are, we'll subtract. Well, we've done this problem before. It's the same shape. It's the same circle equation. The equation of the circle was x squared plus y squared is 4. So solving for y, it's the same as we had at the end of the last video, plus or minus square root of 4 minus x squared. So that means that the base is equal to, it's the y at the top minus the y at the bottom. And so that's the positive root minus the negative root. And just like the last problem, we'll get 2 times root 4 minus x squared. So there's nothing new there. That's the base. The challenge here is to find the height of that triangle. So I'm going to draw that triangle, but instead of trying to deal with it in 3D, we'll just draw it in 2D. So the bottom here we said was B, and then we've got this dotted line here, which we're calling H, and we're trying to figure out what the height is. So what is the height? Well, if we believe that B is the whole bottom side, then probably we could buy into the idea that this is half of B, right? It's equilateral, so lots of things are equal. So that's half of B over there. This side right here, how long is it? Well, it's an equilateral triangle, so it's also B. So I think from this, we can figure out what the height is in terms of B. So we'll get H in terms of B. And then the nice thing is that we already know what B is in terms of X. Ultimately, X is our goal. But we can get B in the interim, and then we'll get over to X. No problem. So Pythagorean theorem to this triangle, and it says H squared plus B over 2 squared, parentheses are mandatory there, is equal to B squared. H squared plus B squared over 4, B squared over 4 equals B squared. Again, the goal was to find the height, so we're going to solve for the height. So subtract B squared over 4. You have 1B squared currently. Subtract B squared over 4, and we'll get 3/4 of B squared. And then finally take the square root. And technically plus or minus, but H is a positive number because it's a length, it's a distance. And we can clean this up just a tiny bit, missing my squared here. So B squared is a perfect square. We'll bring that outside as B. 4 is also a perfect square. It stays on the bottom as a 2. And we get B times the square root of 3 over 2. And actually, that might sound familiar to you. We didn't mention it, but this is a 30, 60, 90 triangle because it's equilateral. So all the angles are each 60. So if you happen to have already memorized the 30, 60, 90 triangle sides, then you could have skipped this part. So I think we're good to go. Let's go ahead and jump over to our area formula, our volume formula, I should say, right up here. So this is equal to, I'm running out of space. Let's put this in here. So the volume is equal to integral of the area function. So we said that the area of a triangle is half base times height. So I'm just going to write that now. Half base times height. And then this will be a d something. Apparently it's dx because we've got x's floating around everywhere. And let's do one more substitution here. This is the integral of 1/2 of, and instead of h, let's go ahead and put this thing we found in red at the bottom. So it turned out that h was equal to b root 3 over 2. So let's plug that right up here at the top. B root 3 over 2. So that's there. And then I'll squeeze this dx in at the end. Okay, so I've got that. Let me clean that up. I'll put it down here below. So we're going to mush together the b's and the 2's and the radical 3. So we've got a b squared root 3 over 4. So let's put that down here. B squared is here, root 3 over 4. I'll put that in the front. It's constant, dx. Okay, and now we're ready to replace the b with the x's, which is that bottom green thing there. We realized that b was equal to 2 root 4 minus x squared. So let's put that in here. Root 3 over 4, integral, we said it was 2 root 4 minus x squared. That was b, but b is getting squared, so it all gets squared. And then finally, we need the limits of integration. So we look at our triangle picture and we imagine sweeping that triangle left and right. So how much is x at the far left? It's -2. How much is x at the far right? It's +2. So we're just going to go from -2 to 2. You could choose to go from 0 to 2 and then double it using symmetry. That's fine. So it turns out, again, you can find this integral without technology, but it's late and I want to go home sooner rather than later, so let's just type this one in, math 9. Okay, so we've got the square root of 3 over 4, I'll put that here, square root of 3 divided by 4, and then times integral 2 square root of 4 minus x squared. Close the parentheses. Am I doing this right? I am not doing this right. You guys need to stop me when I'm not doing this right. Okay, so that's times 2 root, okay, and actually we probably need parentheses there too because we're going to square. So maybe that's okay. Root 3 over 4, 2 root 4 minus x squared, the whole thing squared. I think that's good, comma x, comma, -2, comma 2. So hopefully we've typed that in correctly. If not, you have no one to blame but yourselves. 18.475. So maybe that's right. I have one more way to look at this. It's in Sketchpad. So here is the circle, x squared plus y squared equals, and the radius is 2. We're going to drop the y-axis flat so we can look at this shape. We're going to look at a few equilateral triangles here. Those are just some representative things. Now we're going to sweep one triangle throughout this picture. And you can see small triangles, bigger, 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 smaller, smaller, smaller. And also there's a lot of numbers happening here. The area of the equilateral triangle is there. The x value is there. We came up with a formula that relates the x to the area of any particular triangle. Let's go ahead and create the solid. Oh, so pretty. So let's speed this up and drag it to the end. So there's our shape right there. And here it's keeping track of the cumulative volume. The equilateral triangle areas all get added together. That's what this integral does. Adds them all up and keeps track here, and by the time we get to the end, we get to this 18.48, which matches with what we had over here. So 18.48 cubic units, whatever they are. Okay, number 13, find the volume of the solid whose base is the right triangle pictured and whose cross sections perpendicular to the y-axis are semicircles. So we've got this triangle. Now the cross sections are perpendicular to the y-axis, and they're supposed to be semicircles. So for example, if you pick this point right here, you're going to draw a semicircle where the base of the circle, base of the semicircle is there. So it's going to be a little tiny semicircle, and it comes out of the board like that. And if we were looking at this spot, then it's going to be a bigger semicircle. And if you pick this last spot, you'll get the biggest semicircle of all. And that's what the shape is going to look like, just a bunch of shaded in semicircles. So the question is, what's the volume of that shape? So let me undo one of those. And we're just going to pick a generic point y. And again, the goal is to find, so crossing this off, this is now number 13 here. The goal is to find the area function in terms of y. What's the area of each circle in terms of y? Whatever we get here, we're going to stick into an integral. So let's see if we can do that. First, it's a semicircle. So the area of a full circle, pi r squared, but this is a semicircle, so it's 1/2 pi r squared. Okay, I've named it as an r. Let's go ahead and come in here and name it as an r. So how about we say from here to here? That right there is the radius of our semicircle. And then we ask ourselves, is that an x distance or a y distance? What's changing as you run along that radius? So as you run from here to here, the x is changing. So it seems like it's just an x. All right, well, somehow we got to get this line, the diagonal line segment, into play. So how about we come over here and we say that this is some generic point x comma y. Not really so interested in the x, but I think we'll need to use it. So I guess what I can say is that if this is my number x, then how does that relate to the radius number? Well, it's half. So the radius of this circle is just 1/2 x. This was x. This right over here is half of x. So the radius is half of x. That's going to take us pretty far in terms of getting this guy somewhere we can deal with it. The radius is 1/2 x. And still squared. So I'll go ahead and clean this up just so it looks a little bit nicer. The 1/2 gets squared. That becomes a quarter times the 1/2 that's in the front. So hopefully you guys agree it's a 1/8 pi x squared. So everything's hunky-dory there, except the problem is that we need this to be a function of y. Y is the driving variable. It's going to push these semicircles up and down and sweep out the whole region. So x there isn't very useful to me. We need to get it in terms of y. So how are we going to relate x and y? The only place that I see x and y next to each other is right here. So apparently we're going to have to come up with the relationship that gives this line. So this problem boils down to finding the equation of that line. So I will leave it as an exercise. You can pause the video here if you want. We'll just zip to the answer. So the equation of the line is equal to, or is, y equals. So the slope of this line is -3/4 x plus b. The y-intercept here is 3. So that's the equation of the line. And what we were trying to do was get this to be only y's, which means I want to get rid of that x and replace it with y's, which means I want to solve this equation right here for x. So subtract the 3, multiply by -4/3. A couple of steps in one here. So we get y minus 3, and then multiply by -4/3. I'll go ahead and distribute. So that's not right. That's close. This should be a y. And that's the key that's going to open the door to finishing this problem. So what we're going to do is replace this x right here with all of this stuff, which is exactly the same as x. So area of y is now equal to, it was 1/8 pi x squared. It is now 1/8 pi times all of that red stuff squared. -4/3 y plus 4. And it's getting squared. So then, I mean, that's the hard part. That really is the hard part. The rest of this is mechanical. So the volume of that shape, that solid, is the integral of the area function, dy, going between some number and some other number. So copying that down, integral of 1/8 pi, -4/3 y plus 4 squared dy. And then the last piece is to find the c and the d, the limits of integration. So go back up to your lovely picture. Imagine taking the y and sweeping it up and down. So what's the smallest y, which is down here? That's 0. What's the biggest y that we can plug in? It's 3. So 0 and 3 are our limits of integration. Okay, I'm going to stop with this problem here. You're welcome to solve it using your favorite technology. You can also solve this one by hand without using any technology, which is cool. But we'll end that one there. And say that the homework assignment now is officially assigned. It's this right here. And I'll collect that after the break. So you can bring that to me Monday morning when we come back from spring break. There's a reading assignment for the next section, which we're about to start. So if you haven't done the reading assignment and you'd like to, this would be a good time to pause the video. Questions of the day are there. Project 5 we said was assigned officially today. Project 4 is due right now. Throw it under my office door. And we move on to the bottom of page 26. Number 1, we now study a method of finding volumes of solids that are created by revolving a 2D region about a line. The line is called the axis of revolution. Number 2, name the objects that you get if you revolve the following shaded regions over the given axis of revolution. So we'll do the first one together, and then you should pause the video and try the other three. So we're going to take that rectangle, we're going to revolve it around the line. And what does it look like? So I'm going to draw a copy of that rectangle down here. And then what will it look like? Well, it's going to be spinning all the way around. I think I can do better than that. All the way around there, and then all the way around here, and then behind, something like that. So what shape is that? That's a cylinder, right? It sweeps out the entire shape cylinder. So pause the video here, and then come back once you've drawn the other shapes and named them. Okay, so we've got four shapes up here. The top right one is a sphere. The bottom left one is a cone. That's what you get when you take a triangle and swivel it around a line. And then the bottom right one is, well, it's like a cylinder because it's like the top left one, but I guess it's a cylinder with the hole in it. So you can just say cylinder with a hole, but I'll say cylinder with a cylinder cut out. Okay, so let's move on to the next page. Number 3, for each figure above, draw a slice perpendicular to the axis of revolution and trace the slice as it revolves around the axis. What kind of shapes do you get? So we're coming back to all that stuff we looked at in the last video with the slicing. So we're going to draw a slice perpendicular to the axis. So any random thing, technically it's a rectangle that we're drawing, and then swinging around. It's okay if you just draw a vertical line because this is supposed to be a thin, thin rectangle. So if we take that rectangle and we sweep it all the way around, and we get, well, basically a circle, but I don't want to use the word circle because circles are just the outlines of the shape. This is a filled in thing, right? Because that rectangle is a solid thing. And so the slice is filling in. So it's not just the circle, the boundary, but it's also all the stuff inside the circle. And we're going to use the word disk to describe that. And then the same kind of thing over here, if you take a vertical slice, something perpendicular to the axis, and swing it around, you get another disk. And if you take a slice perpendicular here and you swing it around, you get yet another disk. If you take a slice here, make sure you stop at that spot. You're not going all the way into the white space. And you swing it around, it's going to end up down here. And this one is not a disk, but if you are mechanically oriented, you might have a good name for this kind of a shape. And we're going to use the name washer to describe that shape, disk with the hole in it. So maybe we can write those answers. So we had discs and a single washer. Okay, let's come down and take a look at this next picture here. So there isn't any text, but just the diagrams are supposed to say a lot of stuff to you. If you have a random shape, not something nice like a rectangle or a triangle like we just did, and you swing it around, you can see that, whoops, you can see the arrow there is supposed to tell you you're swinging around the x-axis. Then you get this kind of nice 3D tulip-shaped object. And there is a representative slice, and it is swiveled around, and you end up getting a disk. Same kind of thing for this crazy shaped region. It looks like it's got kind of two different boundaries on it, and we're going to swing it around, and it comes down here, and now instead of getting a nice tulip shaped thing, we get the outline of the tulip, but then there'll be this big hole in the middle like we had with the last picture on the previous page, and instead of having a solid disc, you have a washer right there. And so this is kind of a tulip cut out of a bigger tulip, 3D things. All right, number 4. For obvious reasons, the method that we'll use to find the volumes of the solids from the last example is called the method of disks and washers. Let's take a quick look at some stuff on a Sketchpad file. Okay, so we're going to take a look at this slice right here. We're going to spin it around this axis of revolution, and it's going to trace out a disk. And that's going to be the heart of this method. So there it is. Let's take a look at this one right here. Suppose that this filled in region is the region that you're going to revolve around the x-axis. So you might imagine what kind of a shape you might get if that happens. The idea here is to revolve the rectangle around, and so we get a disk just like that. It's a very thick disk in this case, and if we showed all of them, then I guess we could say that the volume of the 5 disks added together will approximate the actual volume of the solid that we're imagining you get when you rotate this guy around. So we, again, end up with kind of a tulip-shaped solid, and the volumes of these 5 things, you know, do they under or do they over approximate? I think each of these ones is an over approximation, but it's pretty close to the volume of the actual shape. And how would you get closer? Well, instead of using 5 disks, you'd use 5 million disks. And so I'm hoping that you start to feel that the integral is going to help us here, because the integral is about taking, you know, slicing a region and cutting it into a bunch of teeny tiny pieces and then adding up something about those pieces. In this case, we're going to be now adding volumes of these disks. Okay, and then one more. This is the same idea, but in this case now the axis of revolution is here. You're going to revolve this blue space around this axis, but that white space is not part of the action. So imagine in your mind what's going to happen. We're going to click this button. We're going to take that thing, swing it all the way around, back behind the screen, and then up to the front. And so this is like a tulip within a tulip. We've got some space missing in the middle. There's a cylinder cut out of this shape. But the idea is the same. And now we can think about using you know, some disks in order to approximate the volume of this shape. So let's try an example in number 5. Find the volume of the solid that is obtained when the region bounded by y equals square root of x equals 1, and x equals 4, and the x-axis is revolved around the y-axis. So the first step with all these problems is to draw a very good picture. So pause the video here, try to draw a picture without using any technology. These are curves and shapes that we should be able to draw. Frankly, I think it's probably faster to draw some of these without technology. So pause the video and come back when you think you've got a nice big picture of the region enclosed by those curves. Okay, so that space in between is the region that I'm interested in. So it's all of this space right in here. And it's enclosed by all 4. We needed 4 things, 4 boundaries to enclose this region. So we had y equals square root of x, that's my blue curve, x equals 1 is the vertical line, x equals 4 is the other vertical line. We also need to know the x-axis, because if we're not stopping it at the x-axis, then technically this region can go down forever, bounded on both sides by the red lines. So we do need all of those to bound the shape. So we've got that region. Recognize that it's probably going to take a few attempts the first time you're seeing a region to draw a nice big version of it. You really want to have a big region that you can draw in. So it could take a few attempts. All right, so the basic idea here is that we're still using the formula from last class, that the volume is going to be the area of, I'm not even going to put a letter in there, but it's the area function in terms of some variable, go between c and d. Maybe it's x and x, maybe it's y and y, but that's what we're after. So we're going to draw a slice, just a generic slice any place. So I'll call this some generic x. Go up here, Technically, I should draw a little thin rectangle for my slice, but I'm just going to draw that vertical line. And then we're going to take that thing and we're going to rotate it around, revolve it around the x-axis. So what I'm actually going to do is draw another copy of y equals square root of x reflected down there. And we can extend our boundaries this way. And then we're going to take that green slice and we're going to spin it all the way around the x-axis, and it's going to go down there to the bottom, and then it's going to go behind the screen up to the top. So that right there is a disk. And that is the disk whose area we want to find. So I will say it's the area of a general disk, because we're doing it at x, not at a specific number like 1, 2, 3, or 4, but a generic x. So let's go ahead and find the area. So it is a disk. It is a circle, but enclosed. Area of a circle is pi r squared. So let's think about what the radius might be. Is this green thing, that's the radius, is the green thing an x distance or a y distance? And I will put something else in this picture. I will call this point right up here some x comma y, same x, but some arbitrary looking y. And is that green length, is it an x or a y? Hopefully we see it's a y. So then I'll come back here to my pi r squared and say, okay, really it's pi times y squared. And that would be great, we'd be done if this were going to be a y integral, but hopefully we're starting to get a flavor for when it's going to be an x and when it's going to be a y. We're going to sweep this disk left and right, not too far over here, but it's x is the driving force for this one. So we need everything to be x. So the problem here is that we need to make this in terms of x. All right, so then how much is y in terms of x if you're sitting at this point right up here at the top? Well, y is there. Y is equal to the square root of x. So in this case, we don't have to do a lot of work. We just have to replace. So this now becomes pi times square root of x squared. Super. So now I think we're ready to throw that into an integral. So the integral we had up here now becomes volume equals integral area function of x. It's right down here, pi square root of x squared dx. And now again, think about sweeping that purple disk left and right. Where does it start at the far left, the smallest x, and how big does it get at the far right? Those numbers are given. They're 1 and 4 in this problem. Okay, so again, that's an integral that's easy enough to just find by hand. We're going to move on to the next problem, but whatever that thing is, that's the volume of this crazy kind of tulip-shaped thing. Next page, how do things change in the above example if we revolve the region about the line y equals -2? So again, draw another good picture. You can pause the video here if you want to. We're just drawing exactly the same thing as we did before. So it's the same region, but now we're going to spin around a different line, about the line y equals -2. So I'm going to put y equals -2. That is a horizontal line. It's down here, and I'm going to draw it in right there. So when I take my region is still this stuff up here at the top. When I take it and spin it around, there's going to be this white space in between, which means there's going to be white space here, and that region is actually going to come this way. So if I want to draw another copy of the thing from up above, I gotta throw it down, not just flipped over, but I need to have enough space in here so that there's 2 missing on either side of that line. So my new picture actually, I think, is gonna start down here and then go that way. So let's see, the old x-axis is now gonna be down here at y equals -4. So I'll draw that in black. So that's this part. And then the same vertical things, ignore the fact that the picture above has very little resemblance to the picture down here. In theory, this region is supposed to be the same as that region. And we spin it around, and I will draw a representative slice here. We pick any old generic x and draw the slice. Don't draw the slice to the axis that you're spinning around. Just because you're spinning around this line doesn't mean the slice goes to that line. Slice is completely inside the region. And so we take that region, that slice I mean, and we spin it down here. And so we get this inner circle and then this outer circle. And we have ourselves not a disk, but a washer. So goal here is to find the area in terms of the same x, but in this case, it is a washer. So how do we find the area of a washer? Well, the washer is just a big circle with a little circle cut out of it. So what we're going to do is area of the big circle minus area of the little circle. And we're going to symbolize this. We know it's pi r squared. I'm going to use pi r squared for the little circle. I'm going to use pi capital R squared for the big circle. And in fact, every time we have a washer problem, it's going to look like that. Pi capital R squared minus pi little r squared. So this equals pi times something squared minus pi times something squared. So let's find the second something first. I want to know what the little radius is. That is to say, what is the radius of this circle right in here? So the radius of that circle is from here to here. It's also from here to here. And then you ask yourself, as you sweep that purple circle left and right, does it change size? And the answer is no in this case. Purple circle is always touching the x-axis and has a center right there and then is touching down here. So the radius of that circle is always, in this case, it's 2. So that part's easier because it doesn't change. So the radius of the inner circle is 2. The radius of the outer circle, I'll draw this one in purple now. Radius of that circle goes from the center up to the top, or if you prefer, the center to the bottom. So how far is that? Let's see. I guess I'm going to break that purple line segment into 2 parts, cutting it right there. From here to here, I know is always 2. From here to here, is it x or is it y? That's y. And we know what y is. It's the square root of x. So the big radius, a little more space here. I'm going to say the big radius is whatever the y value is at the top, plus 2 more, that blank space in the middle of that washer. So it's the y at the top plus 2. And just like we did before, we can't have y's here. We need to have x's ultimately. So that will be just 4 pi. Instead of y at the top, we're going to put the square root of x. So it's the square root of x plus 2. And I think it's super important for these problems to have a very good, very big picture. I think that it might be tempting to try to think, okay, I'm going to just memorize some formula that will apply to every washer problem. And I think I've got a formula down here for you to try to memorize. There's one right here, pi times integral of f of x squared. On the next page, there's this thing right here. And this actually kind of looks like what we just did. It's some function squared minus some other function squared with a pi factored on the outside. So I think that actually, that is kind of what we did here. I see it. I see pi times some function squared minus, well, this was a pi times some function squared. Happened the function was just always 2. But I really think that it's not worth trying to just memorize some formula. There's no one-size-fits-all thing that we're going to be able to do here. So draw a good picture, really focus on trying to understand this idea of sweeping and finding the area of a slice. In this case, the slice is, the area becomes a washer. And then once we've got that, all we need to do is stick this into an integral. So we're going to take all that stuff, pi root x plus 2 squared minus 4 pi. The whole thing is in the integral. It's a dx. And as you sweep our washer left and right, x starts at 4 and starts at 1 and ends at 4, and that's it. Again, I think it's possible to do this integral without technology, so that would be good practice. You're also welcome to just type it in, and whatever you get is going to be the volume of this tulip, but with a cylinder cut out of it. Okay, so right down here we've got this formula. It says if you're doing the disk method, and the slice is perpendicular to the axis, don't worry about that for right now because every problem in this section, the slice is going to be perpendicular. You could see it up here. the purple line, this one here, was perpendicular to the axis that we were spinning around. But in the next section, that's not going to be true anymore. So you don't need to worry about that perpendicular stuff for right now. Soon enough, it will come into play. But if we have a disk, then you just do pi times the integral of the function squared. And I think we did that on this previous problem here. Take a look at what we ended up integrating when all was said and done. Pi times the function in this case was right here. It was the square root of x. Pi times the function squared. Pi could always just come out to the front. That's what it looks like in the formula. And then in the problem that we just did, the formula is on the next page. It's pi times pi on the outside. You can factor it out. One function squared minus another function squared. That's what it turned out to be. This was one function squared. This was the other function squared. It happened that the other function was just always 2, but it could be something with x's in there. All right, so let's try number 7. There's a hole here, just like in the previous problem. Find the volume of the solid generated when the region between the graphs of f of x equals 1/2 plus x squared and g of x equals x is over the interval 0 to 2 is revolved about the x-axis. So again, pause the video here. Take your time drawing a good picture. It might take a few attempts before you have a nice picture with lots of space in it. Okay, so there's my region. It's the space that's inside of all of this here. Again, you do need to have all of the boundaries given to you. So it's capped at the right by 2, it's capped at the left by 0. That's this part right here. At the top, it's that parabola, and at the bottom, it's that line. So we've got our region. We're going to take this thing and swivel it around the x-axis. So take it and spin it around this axis. Doesn't make any difference to me that there's a hole there in the middle. We're just going to draw a representative slice. So we'll pick a generic x kind of thing. How do I know my slice should be vertical? Well, I guess we don't quite know that yet, but what we said is that everything today is perpendicular to the axis. So let's draw a slice perpendicular to the axis. Notice the slice is only in the region. You're not going to draw this part. That's not going to be part of the final shape. So we'll go ahead and draw a carbon copy of this picture down below. Doesn't need to be super precise. And then that slice gets copied as well. It has a counterpart. And then we're going to connect the dots, connect the two slices. So this bottom part of the slice makes a circle with the top of the other slice, and then this one gets matched up with its partner down at the bottom. And lo and behold, what shape do we have when the slice is rotated around? That is a washer. So every washer problem is going to be the same for us. Big part of this is to draw the picture and then figure out what the slice is doing. So the area of a washer, we'll just jump to the pi times big R squared minus pi times little r squared equals pi times. Okay, so how much is the big radius? Let's draw in something. We'll draw in, I need another color. I only have, all right, we'll draw in red. So actually we'll do blue. So the big radius of this washer, so there's the center of the washer, and then there's the edge of the washer, the extreme edge. So how long is that? First, decide if it's an x or a y. Okay, so as you run up and down, y is changing. So that's a y distance right there. How much is y up there? It's given by the function. It's 1/2 plus x squared. Okay, so pi times 1/2 plus x squared. That is the function. According to the formula, it is supposed to be squared no matter what. Minus pi times some little r squared. Little r we're going to draw in red. So it's the radius of the inner circle. The center is still there. Now the inner circle just goes to there. Is that an x distance or a y? That's a y. How much is y? Well, that's easy. Y actually happens to be exactly x because that's this function. So pi times, it should be a y, but it's the same as x. That gets squared. All right, hunky-dory. We stick this into an integral, just as is, pi times 1/2 plus x squared squared minus pi times x squared. There's a dx, brackets around the whole thing. And I'm going to go ahead and pull those pi's out. You're welcome to leave them in, or you can factor them both out. It's a little bit cleaner if they all come out to the front. That. And then sweep the x, sweep that purple washer left and right. So as you sweep it to the left, how much is x at the far left? How much is x at the far right? It's 0 and 2. So those are the limits for the integral. So pi times that integral from 0 to 2. Again, you can do this one by hand or with technology. Whatever you get is the volume of that crazy three-dimensional shape. All right, and then we can go to the next page. We'll see a formula that is hopefully really starting to jive with us. Pi on the outside, function squared minus function squared. Let's take a look at the very last thing we wrote down here. Pi on the outside, function squared minus function squared. Big function, little function, high minus low. It all boils down to just the area of a washer. It's pi times the big circle, the big radius squared minus pi times the little radius squared. Okay, next problem is number 9. It says we can equally spin things about the y-axis. Find the volume of the solid generated when the region enclosed by y equals square root of x, y equals 2, and x equals 0 is revolved about the y-axis. Again, pause the video, see if you can draw a nice big picture. It might take a couple of attempts, but try to draw it without technology. Okay, so we've got our three things. Square root of x is my blue curve. Y equals 2 is this horizontal red line. X equals 0, we need it. It's that, the y-axis. So there's my region enclosed, and we're going to revolve this about the y-axis. So we're spinning this way now. So I'll draw a carbon copy of this over here to the left. And now this time we're going to draw a slice, but again today the slice is always perpendicular to the axis you're spinning around. So in this case I'm not going to start with a generic x and then draw here. What I'm going to do is start with a generic y, some random point, and then draw my slice there. And as I take that slice and spin it around the y-axis, goes around and then behind. It doesn't look very good. Comes around and then goes behind. Good enough. So is that a disc or a washer? It's a disc. There's no space in the middle of that thing. So what we need to do is find the area of the disc. Still pi r squared. Capital, lowercase, doesn't matter. There's only one r in this problem. So the radius is the length of that green slice. So would you say that the length of that green slice is an x length or a y length? And hopefully we recognize it's an x length. And just for kicks, we'll go ahead and label this point right here, some x with some y. I guess I should have labeled that point on the y-axis with a y. So first thing we're doing here is saying that the radius is really x. So it's really pi times x squared. But that's no good because this integral that we're going to do hinges on that purple slice moving up and down. And the fact that y is the driving force here means that the integral is going to have y's, and it'll be a dy integral. Okay, so what do? We need to find this thing in terms of y. So how do you relate x and y? Well, xy is this point that's on the curve. Here's the equation that tells you everything there is to know about the curve. So what we need to do is solve this for x. Square both sides, we get x is y squared. So that means that the area of the disk is equal to pi times, it used to be x, something is funny here. I meant to put this, it doesn't matter, but I meant to put this square on the outside. Okay, so it should be pi times whatever x is, and then it should be squared. So I've got the pi, I've got a blank where x should be, and then that's the squared. So how much is x? Well, apparently it's y squared. So this guy goes right in here instead of the x. So right there we go, y squared. Okay, so easy to clean this up, we may as well do it. That's pi y to the fourth, and that's the thing we're going to stick into our integral. So the volume of this lovely tulip we've drawn, integral pi times y to the fourth dy, and now we got to put the limits on the integral sign. So imagine taking that purple slice and sliding it up and down. At the bottom, how much is y? It's 0. At the top, how much is y? It's 2. And this integral is so easy to do, we may as well just do the darn thing. So pi times y to the fifth over 5 between 0 and 2. Pi times 32 fifths minus nothing. So the volume of that wonderful tulip is 32 pi divided by 5. All right, number 10. If you're into memorizing things, this should help you set up your integrals. If your slice is vertical, not this example, but previous examples. So here our slice was that purple thing, or I guess ultimately it was a green thing. It was that was our slice, was this green line right here. So if your slice is vertical, then what happens? Well, what happened is the final integral was in terms of x, right? This was a dx integral, and the slice was vertical, and that's always going to be the case. If your slice is vertical, it's a dx. And the other thing that means is that what you need to do is, originally it'll be a y, but it needs to come around to something with x. So you had better, at some point, solve your equation for y. In this case, the equation was just y equals square root of x, right? It was already done, so we didn't have to do anything. But you have to solve for y no matter what if it's a vertical slice. So let's see what kind of creative mnemonic device I came up with. If your slice is vertical, you will solve your equations for y. So we just talked about that. And the integral will be of the dx variety. So I don't think they have any of these stores around here, but I used to grow up, or I grew up in some place where there were Winn-Dixies around. It was just a grocery mart. And so if it is a vertical slice, v, then your integral is going to be dx, Winn-Dixie. What can I say? I was tired when I wrote this. If your slice is horizontal, like the one that we did right up above here, then what ended up happening? So for our horizontal slice, we had a dy ultimately. Y was the driver, which meant that we needed to solve our equation. We needed to get y by itself. We needed to replace the x with y's, which meant we had to solve our equation for x. So horizontal slice, solve for x. If your slice is horizontal, you will solve your equations for x, and the integral will be of the dy variety, horizontal dy. Howdy. All right, well, I mean, it's 7:30 at night, and I really want to go home, so I'm not going to try to improve on that. I'm certain that you guys can. Number 11, yeah, I really do want to go home. We're going to skip 11. We can talk about that after spring break if we wish. And what's on the next page, number 12, neat little website that allows you to easily create your own solids of revolution. Check it out, email me a screenshot if you create a work of art that you're willing to share with the class. I'll give you a point on your next quiz if you email me a solid of revolution by the start of next class. And when I say a point, I don't mean a percentage point, but a full point on the next quiz. So if the next quiz is out of 30 points, you are adding 1 point out of 30. That's like a 3% bump right there. So check out the website if you have some time. Share with me your best work or works of art if you can't choose just one, and I'll give you extra credit. So the homework is there. Questions of the day and reading for next Monday are in the usual place. Here's the reading for next time. Project 5 you are starting to work on, that's the one with the chocolates. It's going to be due the week after spring break. Our quiz is the very first thing that's happening next class. And again, the calendar in the syllabus tells you exactly what sections the quiz is on. So I do thank you for giving me the freedom to go take this trip and give my talks. And I hope that this sort of hybrid version of our class is going to work for everybody. I really do. I will be checking email over break, so if you have any kind of question, please do not be shy to send it my way, and I will respond as soon as I can. Have a wonderful break, and we'll see you guys in a while.